Uh, so my part, as I said, is related to the hydrological modeling. So, and we will then go to the firstly terrestrial part of the Earth system, and so we will talk about the different approaches which are done in the uh, area of firstly river projections. So as far as in this short lecture, it's not possible to combine all different types of approaches which done in the this let's say water related processes. And with the background slide, I choose such kind of philosophical vision on the Earth system, which is related to the maybe most important approach where we need the model. So the thing which we are not uh, typically able to measure is the things which we have to model. And this means that we need to model the changes and the changes both in the past, in the present, and in the future. And that's the crucial type of the approaches which both combine the atmosphere and water science, and which are also give us different way forward in understanding the Earth system in general. And the challenge is related to that we have both rather uniform change and we have the catastrophic change, and that we have the similar process which prevailed in the past and in the present, and that's the basic laws of the nature are time invariant. So these things are let's say more crucial for moving forward. And the next point is that everything is very deeply interrelated in the atmospheric Earth system. And if we try to look at the different governing processes of the hydrological phenomena, then we will see that um, at the end, everything is driven by the climate system. And if we even look on the general water balance equation, we will see that the precipitation and evaporation are the driving forces for all hydrological processes in general. As far as further on, the water discharge is the dominant in all their river related phenomena. But additionally, many other things are important, and starting from the climate and this evaporation and precipitation metrics, we see that rather wide range of different, let's say, processes, parameters, and features are driven by the impact of climate, and then all these combined into the understanding of the hydrological change. And then if sum up this quite complicated graph, we can say that we're interested in looking at the possibility to model and to predict firstly the water discharge, but also many other sub-processes or independent processes, which are usually also governed by the water discharge. And among these processes, there can be such distinct things like erosion, like the water and sediment quality, and in general chemistry, and everything. All this more remote from the traditional amount of water region is at the end is accounted by this climate system. And this is the key points which I would like to discuss in this short lecture, how the uh, interrelated processes are uh, driven, and I would focus on the three main groups of models. Again, with the vision that I just, it will be more introductory lecture, and rather short time. So we'll talk about the flow simulation. So the flow, which is the key points in the climate Earth system in terms of the hydrology, which is directly driven by the climate system. Is the is the mirror of the climate, the flow. And I will talk about the approaches which are used to model erosion, which is the dominant process in mass movement on the surface, and also driving both by climatic system and by the flow on the Earth system. And then we will have a short example of the hydrogeochemical modeling approaches, which are, as I said, also related to hydrological processes, the hydrogeochemistry, but linked to both the flow and the erosion in general, driven then by the climate, but presents completely specific drivers. So then with starting from the flow simulation approaches, there is the wide group of models which are can be counted like the approaches to model flow, and typically they are split in two big groups. The first is the basin models, and the second is the river flow model. So this is very, let's say, this is this scheme is have a lot of assumptions as far as in real life everything is much more complicated. But generally we can say that this division in two main groups are possible. And so regarding the river flow models, we have the few different approaches which enable us to predict the amount of water in the river system and the change along the river system of these flow parameters. But more close to the climatic system, we have the basin models. And so there are two most famous groups, and I would focus on the one of them is the rainfall runoff models. So as it's said, and it's the basic law of the hydrological system is that the runoff is driven by the rainfalls, by the rains. And then this group of models is the number one in the hydrological step of the studies related to the climate change. And a variety of these approaches can be counted in this rainfall runoff modeling tools. And there are three of the K are crucial important. The first is the black box models. They are called as well the empirical models. The white box models, which are called as physics-based models, and the gray box or the conceptual models. Further on, I would mostly show some key examples of how these models used, how they work for the modeling of the hydrological system. And before that, some general comparative things which are related to making this process understandable. So the empirical models are the relationships between the inputs and the outputs, and this is called as sometimes the black box concept, which when we have, for example, the precipitation and on the watershed, and then we have the flow, and we do not know what's done between these two parameters, how the water from which was the precipitation was directed to the river stream and then forms the flow. So that's why this is called like a black box model, black box concept. And we don't know the connection, but for the non-linear relationship, we are able to estimate the sequence, and based on the, for example, climatic estimates of the future precipitation, this is the most robust approach to predict the future flow. The conception models used on the physically based equations, and this is the more usually look like a more simplified equations, and which represent also the water storage in the catchment. In comparison to the physical models, this is more simple approach. Also, traditionally do not account many of the variabilities. And here we come to the most number one in hydrological modeling is the physical models, which are based on the physical laws and equations, and so which try to simulate the real hydrological responses. So in brief, we can say that we follow each drop which comes from the atmosphere to the earth and then proceed to the water. We know the fate of this drop, and we are able to numerically, mathematically describe the process of this drop moving. So what's also the important part of the story of the hydrological models in the variety of specific existed tools, softwares, and sort of commercial and non-commercial models, which were done in all of these three groups. So for the empirical one is the most important tool now is artificial networks, which move forward all these signs significantly. And for the both conceptual and physical models, with the variety of the, as I said, different products which can be used and which usually have the interface and which is capable to be considered in their studies. The traditional conceptual model is something like you have on the screen now. This is the representations of the different links between the process which are considered in such kind of models to capture the water balance in all these different parameters. So so this is like one of the examples of the existing toolbox. And in Russia, the most famous physically based model is so-called ECOMAC model, which is done in the Water Problems Institute, and which is very relevant for both large-scale and small-scale applications. And for your general vision, this model described the process such as snow accumulation, soil freezing, water infiltration, evapotranspiration, different types of the flows by the physical mathematical equations. And this special schematization of the model comes to the conclusion that the user of the model is able to predict the parameters of water flow based on the assessment of the variety of very deep and detailed phenomena which exist on the river catchment. And the applicability of these models and such of this type of models is used is number one in the development of hydrology for the last dozens of years. And the most widely used application of this hydrological modeling in the terms of flow is the predictions of the possible changes of river flow due to projected climate change. And there are two approaches. So the one is that we use directly ensemble of the climate models, and in the global scale especially, these ensembles give us, based on different scenarios, the understanding of the hydrological response to the future climate change. So such kind of predictions are done in the IPCC a lot, and there is plenty of publications which are dealt with this annual mean runoff change for the end of the century. And the most typical output of these studies, which is important to figure out, is that there is the increase of the water flow in the Fanul runoff in the north. If we consider the scale of the Eurasia and the decrease in the south, so the wet north and the dry south, the dominant concept now in this hydrological model predictions. And then we can use such kind of more catchment-based models like mentioned before, like an ECOMAC, and the projection derived from the hydrological models, which are forced by global circulation models data, is the another like direction in all these studies. And there are few also approaches which are considered. In general, there is much more robustness of this approach. There is significantly great precision and accuracy of such kind of predictions, and much more input information is needed. And this direction of the hydrological modeling, hydrological response to climate change, is now applied for many catchments. And then the specific part of this story is the comparison of different physical models results in terms of the accuracy, in terms of the again robustness. And the example of the studies which are related to this comparison of the regional hydrological models is this ICMIP project, which was done with the case studies selected from 14 different catchments over the world. This study is attracted quite big attention of hydrological community, and was able to demonstrate how different physical-based hydrological models are able to predict and simulate the flow in different zones. And then another example which is done, which is maybe the most important direction of the hydrological studies, is such kind of prediction for the different parts of the Earth system. And we have it can be different regional studies can be used to support this or to illustrate this topic. And here I show the results of the particular study on the Northern Hemisphere assessment, which was based on the water balance prediction for different case study areas selected in the northern domain. And the study which also demonstrated the very big difference in the future runoff changes between the northern and the southern latitudes. And then the Russia is summary done by Institute of Water Problems, and it's another example of the very big variability of the mean annual runoff projection for the large Russian rivers under the different RCP scenarios. And this is another evidence of the future regional introduction into building the detailed hydrological physically based models in future. Related to this completely flow and climate driving related topic, there is many tools which can be used to enhance the applicability of these studies. And so with this, I would mention the topic related to our recent project in Moscow, which is done together with Helsinki University with Marco Kulmala, and there is the idea of the integration in the different kind of hydrological with flow routine models with the other sort of the atmospherical driven models. And we used here for the local catchment the distributed with physically based rainfall runoff simulation model, one of these big variety of the models which can be used for that. But the crucial idea that's the water quality model which is exist in this toolbox is compared with the atmospheric deposition estimates which are done based on the Enviro-Hirolam approach. And so this kind of the combination of completely different atmospherically based and surface-based approaches give us a unique possibility to see how to simulate the inputs of the atmospheric deposition, the role of atmospheric deposition, which sometimes can be crucially important in their urban areas, on their water quality and on the hydrogeochemical flux. And this is give us the unique possibility to estimate the non-point pollution load in this case study area due to atmospheric deposition. This is the first part of the hydrological modeling fields or worlds which I have to talk about, and the next part of this lecture will be devoted to the erosion, which is also considered like a hydrological process, and which is driven by also the precipitation and rain and runoff. And this is the thing which is also very popular in some way and very important in their hydrological science now. And generally talking about the erosion, there is studies which are related to a few different types of estimation, and generally there's two kind of models we can develop or consider. There's the empirical models, which are simple structure and which are based on coefficients which are computed or calibrated on the basis of measurement, and again the physically based models. And so it's not just the coincidence that we have the similar road physically based models. Typically, all the physically based models are integrated into the water runoff generation models, and it's like the one tool and the model which is proceeded from the these flow routine models which I talked before. So the most well-known approach which is used for predicting the erosion is the so-called universal soil loss equation. This is on the screen, and this is the equation which very well known as the ASL acronym, and which has the combination of the main drivers of the erosion process, which is simulated then by the knowledge of the flow model. And there is the crucial climate-related things which called rainfall erosivity. In case of the melting water, there will be the additional drivers which related to the force of melting water. But in general, these five components typically give us the number of the possible degradation of the lands due to the flowing water. And this type of the approach is also called like catchment erosion model. And so they are able to simulate the possible wash of the grounds, soils on the surface of the catchment. So the key topic in this is the understanding of the detachment, of the transport, and of the deposition. And so that's the equation, the Asel equation. It's an old and similar approaches simulate the detachment, and further development of all this hydrological modeling tool was related to the simulation of the transport and of the deposition of the particles, how they can be driven in the surface, and if they reach the river system. And in the river system, we will have the hydrodynamic models to predict the flow change. But anyway, in the case of these catchment erosion models, we have the different things which are related in the there is sort of the parameters, and there is many so-called subroutine models which completely oriented to predict the transport of the detached particle on the surface. And generally it's look like that we have some area where the particle was moved, and then it's we need to know the total x, how much of the detached particles goes to the river system. And this sort of the approach, which is combined together again the climate, the surface runoff, the detachment, the erosion of the particles, and the amount of the sediments washed into the river system. There are many sub models and sub different approaches which simulate this phenomena, and crucially they are objective to estimate so-called SDR parameter. SDR is the sediment delivery ratio, and so this is sediment delivery ratio is the number one in this hydrological part of science, related to how much of the detached particles were reached the river system. So this is the sense of these SDR models, and this SDR approaches can be such kind of morphological one, which consider the slope, the gradient, and the kind of topography measures. Or it can be more hydraulic one, which consider also the surface runoff and simulate the power and the transport capacity of the surface flows. And with an example of these things, I would briefly just show the application of this watershed erosion model for the large boreal watersheds in the north of Russia. And this is actually the study which is now on the way, also under the PX umbrella, and in big joint efforts for the northern territories of Eurasian domain. And here we are the first who, in the very big spatial resolution, model the watershed erosion in the biggest, largest catchments of the northern Russia, with the application of the most high-resolution digital elevation models and rainfall data to see how much sediments are detached on the surface of the catchment. And comparatively with the data on the river flows, we can then argue and consider the importance of the catchment processes in the total fluvial export into the polar seas. This topic, which is crucial for our future studies in general, and in particular, we are considering like a novel science, especially in terms of the how much sediments will be and chemical elements will be delivered to the northern oceans. And those who are interested in this part, you are very welcome to join the next year U-Arctic Congress in Moscow, which is particularly aimed to, and the session here will be particularly aimed to study these integrations. And the last part, which I'm interested to talk about under this general hydrological modeling lecture, is the specific concern in the hydrology is the issues related to water or sediment quality and the chemistry of the moving particles by the river water. So, and for that, it's the good point to start from the mentioning the completely another approach from another field of science, which is related to more chemical science. And this is the so-called thermodynamic reactor models. So in the field of different approaches in hydrology, this is maybe the right corner, and it's what I talked before when I started the flow models is the heart of these hydrological fields. And such kind of migration dynamic reactor models are based on the calculation of the mass balance for the substances that react. And they are typically the things which enable us to predict the fate of the chemicals in the river system, which are driven by the sort of processes in the water after their, not by their physically based processes like a movement, like a detachment, and which are driven by their power law or by the gravity. This is the processes which are driven by the chemical reactions. And this approach is also done now in the few are well-known or sort of complicated models, which are have this name of thermodynamic models, and typically they are deal with the two sorts of the substances. It is the dissolved substances, so it is the particulate substances which are absorbed or adsorbed suspension. And these kind of models stimulate the mass balance equation, which is based on the solving the multi-component problems of chemical equilibrium by calculating the systems of linear and non-linear balance equations. So they're typical. The input data is also very different as far as the different chemical reactors are dependent on the physical and chemical conditions. And then to use such kind of approaches, we have to deal with quite big input data. But this is the thing which also then driven by all the previous approaches. And like the full inventory of the input data, which can be called like problems, give us the most and very well understanding of the run of the fate of different chemicals, and they are partitioning between the dissolved and the particulate phases. And kind of studies in there also polar regions revealed that such kind of geochemical approach can be used as the very important step forward from the flow routine or from the erosion models, which deals with the mass balance, to the exact understanding of the in general the terrestrial flux, and in particular on the fate of different models in the river system. And coming to the end of this lecture and making it putting all together, I would make a particular focus on this conceptual diagram, which is somehow the ability to link together different hydrological models and different hydrological processes in the climate Earth system. And this is to illustrate that there is the water discharges, which are primarily driven by the climate system, and the water discharges is the one big area of the hydrological models which have the input data, firstly the rainfalls, and that's why they're called the rainfall flow models. And so they are dealing with the different hydrographs at the ends. And all these water discharge pillars, let's say so, they then give the information to predict different uh, processes in the hydrological system, and the variety of these processes to simulate is very wide, and this can be used uh, like a brainstorm for future research as far as this integration of different knowledges and different physical based equations with these chemical equations as well is what we have to learn in future for hydrological modeling. And this is maybe also the crucial thing in integration for understanding particular processes and problems in the and the recent climate changes in the Earth system. So with this, I would come to the end of my part of the lecture, and again welcoming all the participants and lecturers to this school, and wishing you a good luck with the